Okay, so we've made it to the last part of this standard, and that is that we're going to be finding solution sets to rational inequalities. We're going to be working with inequalities today. And in order to solve inequalities, we have to first figure out some values that we're going to put on a number line so we can do our number line test. Anytime you have inequalities, a number line test is a really good way to check because we're trying to find out if numbers are greater than or less than, and using the number line test to find your intervals is a really good way to do that. So let's get started. So the first thing we need to do is what values do we need to consider and why are we choosing those? So I've got an example here where I've got something, a fraction, that I've got set equal to 0 or it is greater than 0. And we have to consider where will it be exactly equal to 0, because that value needs to be included or excluded if I didn't want it to be equal to 0. So it's an important value. So the numerator will equal 0 when x equals 0. So I need to consider when the numerator equals 0. And this is going to be decided whether or not I use an open or a closed circle. And in this case, I would have to use a closed circle by putting a 0 on my number line, because I want it to be acceptable to equal 0. Okay, the next thing I have to do is look at the denominator. Now the denominator is not going to equal 0. We actually want to avoid it equaling 0. So this is our excluded value. So we set the denominator equal to 0 and we say x cannot equal -2, which means that has to be an open circle. So when the denominator equals 0, this gives us an excluded value, and we want to always use an open circle. So I'm going to put a -2 on my number line with an open circle. So this has created the regions in which we get to test whether or not this fraction is greater than 0. We already know where it's going to equal 0. It will equal 0 at 0. So 0 is part of our solution. We just don't know if we're using a union or an intersection in this case. So the number line test is a must, okay? You have to use the number line test. To not use a number line test means that you're not understanding the inequality and the fact that there are multiple values that will serve as a solution. So let's go ahead and get started. I'm not going to continue that one because we're going to do lots of number line tests together. So here's this first one, and I'm comparing this fraction to 1, which I do not want to do. So to avoid setting this and comparing it to 1, you must subtract the 1 or subtract the constant and simplify to a single fraction, which we know how to do. So I have 5 over x plus 4 is now -1, greater than or equal to 0. Well, 1 can be represented in a gazillion different ways, so we're going to use a very fancy form of 1, and that is that I'm going to use x plus 4 over x plus 4, because that will allow me to combine this and get a single fraction. So now I have 5 minus x minus 4, because I am distributing, over x plus 4 compared to 0, or I have 1 minus x over x plus 4 compared to 0. At this point, I can determine what values I want to put on my number line, and that is when the numerator equals 0, and that would be when x equals 1, or when the denominator equals 0, which means x equals -4. So the two numbers that go on my number line are determined by the numerator and denominator, but you have to go through these other steps first. So -4 and 1. Now, I have to determine whether or not they are open or closed. Denominator numbers are always open because I never want to include a value that will make my fraction undefined. Numerator values can be open or closed depending on whether or not we are including or excluding them. In this case, we are including them, so this one is going to be closed. Listen to that again if you're unsure when we use open and closed circles. Now I'm going to test. And I'm going to test using this fraction down here. So I'm going to rewrite it, 1 minus x over x plus 4, and we are comparing this to 0. So I will test, let's say a negative 5. When you test a negative 5 in the numerator, you get a positive number, but in the denominator you get a negative. And this is not greater than 0. So this is false. The next section, maybe I'll test a 0. If you put a 0 in the numerator, you get a positive number. If you put a 0 in the denominator, you get a positive number, which means that is greater than or equal to 0. So this is included. And then I'm going to test a number greater than 1, like 7. It doesn't matter. And when you test that, I didn't write true. When you test a positive number, I would get a negative in the numerator and a positive in the denominator, and this is false. This does not work. So my final conclusion is that my values are between negative 4 exclusive and positive 1 inclusive. You will not always get a false, true, false. You may get a false, true, true. You may get a true, true, false. You may get all falses. There's lots of different possibilities. So don't just jump to a conclusion right away. Make sure you test every interval. Let's try another one. All right, once again, we have to move the 5 and simplify to a single fraction. So I have 2x minus 1 over 3x plus 4 minus a 5 is less than 0. And I'm going to use a fancy form of 1, and that is 3x plus 4 over 3x plus 4 because it allows me to get the same denominator. But I have to multiply this 5 on the numerator. So 2x minus 1 is minus 5 times 3x plus 4 less than 0. And that means each of these is over 3x plus 4. Which means I really only have one fraction. And I'm going to distribute a negative 5. So I have 2x minus 1 minus 15x minus 20. And when I combine like terms, I have negative 13x minus 21. Awesome. So the next step is to determine what values go on my number line so I can do my interval testing. It doesn't mean they're going to be pretty numbers, but we have to use them. So in the numerator, negative 13x minus 21 equals 0. Negative 13x equals positive 21. X will equal negative 21 over 13. All right. To find an approximation of that, it's just under negative 2. So I will put negative 21 over 13. It's in the numerator. We'll do that in a second. Let me do the denominator first. Okay. So now I have 3x plus 4 equal to 0. Subtract the 4. Divide by the 3, so x equals negative 4/3. Well, also, negative 4/3 is larger or closer to 0, so negative 4/3 will go on this side, and you can get a decimal approximation to figure out the order. Now remember, my denominator is always an open circle. My numerator in this case, because I have an exclusive symbol, my numerator is also an open circle because I do not want it to equal 0. So we're going to compare using this one, and I'm not going to use fractions to test. I'm going to use some nice whole numbers if I can. And if I can, it doesn't mean I can. And it looks like on the far side, let's use negative 4. Let's just pick something I know is significantly smaller, and let's test a negative 4. When you substitute in a negative 4, the numerator is positive, but the denominator is negative. This is less than 0. This is true. Remember, I'm plugging in a negative 4. The numerator is going to be positive when I do that, but the denominator will be negative. This is true. It is less than 0. Choosing a number in between here, I'm going to actually test negative 1.5. Okay, so in my numerator, when I substituted a negative 1.5, negative 13 times negative 1.5 minus a 21 is negative. And when I substituted a negative 1.5 into the bottom, 3 times negative 1.5 plus 4 is also negative. So a negative over a negative less than 0 is false, so I will not shade in between. And then I'm so excited that I get to use 0 on this side to test. And when I do that, I get a negative over a positive less than 0, and that is true. All right, take your time if you need to on those testing. I am simply substituting in and using just a little bit of a number sense to know that if I multiply a 0 here in the numerator, it's negative, and a 0 in the denominator is a positive, and a negative divided by a positive is negative, so it's less than 0. So I might be going through that a little bit faster, but I'm simply using some number sense. All right, my final answer then is from negative infinity to negative 21 over 13 exclusive union with negative 4/3 to positive infinity exclusive as well. All right, I think we've got one more to try. All right, so this last one, it's already set equal to 0 or less than 0, so I don't have to move anything, I don't have to combine terms, I'm ready to decide what numbers go on my number line. So I set my numerator equal to 0, and I get x equals 8/9, so that's going to go on my number line. I don't know where to put it yet. I'll put it right here. Okay. And because it's exclusive, I'm going to put an open circle. Now I go to the denominator. 4x squared plus 25 equal to 0. And when I start solving using inverse operations, I notice that I'm going to get a squared value equal to a negative number, which is not possible in the real number system. And I am working with real numbers because I'm going to a number line. So I actually have no values from the denominator where this will be undefined. So this is never undefined, which means the only value that goes on my number line is 8/9. So I have to test on either side of that, making this very simple. My denominator will always be positive. 4 times a number squared is always positive, and plus 25 keeps it positive. So I will test something smaller like 0. If I put a 0 in the numerator, I get a negative, and if I put a 0 in the denominator, it's positive, which is less than 0, so this is true. And then I'm going to test a number on the other side, which like positive 1, and if I put a positive 1 in the numerator, I get a positive, and a positive in the denominator. That is not going to be less than 0. This is false. So my only interval is not a union, it's not an intersection, it is simply negative infinity to 8/9 exclusive, and we're done.